Hi everyone, welcome back. Now this is the only way I really see shear strain, at least an easy way to look at it, and it's with these kind of vibration isolation mounts. So you might have a machine that vibrates a lot on top of this, but you keep it from vibrating your table through these isolation mounts. And they are affected by shear strain. They get deformed and their cross-section changes, as you can see right here. Okay, with that, let's read the problem. So we have 16 by 22 by 25 millimeter rubber blocks, which are shown right here. And they're used in a W shear mount to isolate the vibration of the machine from its supports. We have an applied load P of 690 newtons, which causes the upper frame to be deflected downward by 7 millimeters. And it says determine the average shear strain and the shear stress in the rubber blocks. Okay, so with that in mind, I want you to pause, try out this problem, see if you can solve it, and then come back and tell me how you did. So, 3, 2, 1, and you're back. Let's try it together now and see how you did. Okay, first off, let's consider the deformation of one block after a downward deflection of 7 millimeters. So we redraw it, okay. 7 millimeters right here, we have 22 millimeters as the original length. Actually that's the height, and then we have the 60 millimeters right here. Okay, Now remember that we always use the small angle approximation of tan of gamma is equal to gamma. And so that's always opposite of adjacent, so that's the 7 over the 16. Okay, 7 over the 16, not the 22. That is not part of this angle at all. It does not help us at all. Be very careful about that. So this comes out to be 0.4375. And therefore, gamma is going to be 0.412410 radians. Now, if you're wondering, why didn't we use the whole tan of gamma is equal to gamma this time? We'll come back to that. So in this case, the shear strain in the block would be 412,000 microrads. And because of that, this is definitely not a small angle. Now let's just check for a second and see how far off it would be if we were to have to make that approximation that tan of the angle is equal to the angle. Okay, so let's see, we have 7 divided by 16, and if we're lucky, that should equal 0.412, which it's not going to. I'll go ahead and pop up my calculator. 7 divided by 16. 7 divided by 16. 0.4375. Okay. Really should have guessed that. Sorry. And see, there is a significant difference here. They should not be different at all. Okay, now with that in mind, we have calculated the shear strain, which is 0.412 rads or 412,000 microrads. Now we have the applied load of 690 newtons, but it's carried by 2 blocks. Therefore, the shear force of one block is simply half of that. If you're really uncertain, draw out your free body diagram. Remember, you're going to have this U, okay? 690 is coming down. You're going to have 2 shear forces going up. Be on one side, be on the other. And those are holding it in place. Now, what area is subjected to the, what area is holding this shear force? Well, it's going to be the area that is parallel to the direction of the shear force. That'll be the 22 meter by 25 millimeter surface of the block. Therefore, our shear stress is equal to our shear force over the area, and so it will be 0.627 megapascals or 627 kilopascals. And there's a little picture to show you what I was talking about. We have 2 shear forces on either side, and this would be the area that would be holding it, the side area, not the 16 millimeter side. Okay, so that's it for this time. Thank you for watching, and I'll see you all next time. Bye-bye.